Hi students. So now we are discussing the ring concept. Okay. So ring theory is a branch of mathematics. It should be studies some mathematical structures. So these structures consist of a set occupied with a set of some set of some binary operations plus and generally it is called plus addition and multiplications that should be satisfy the certain axioms. Okay. So now let us redefine the definition of ring. So first we take the non-empty set. Non-empty set capital R is said to be ring is defined by in plus and dot plus and dot is satisfy the some axioms following axioms satisfy the following axioms. So first one R comma plus is an abelian group. So abelian groups it contains 5 axioms. So closure means for any element a comma b belongs to capital R. So a plus b belongs to R. For every a comma b belongs to R. So that is a closure axioms. And second associative. So associative for every element a comma b comma c belongs to R. So associative axioms a plus b plus c equal to a plus b plus c. So that is the associative axioms. Next, identity. So identity property is under additive. So under addition, 0 is the identity element. Okay. So 0 belongs to R. So the identity axioms for any element A belongs to R. Okay, such that A plus 0 equal to 0 plus A equal to A. So identity axioms. Next, inverse. So inverse is for any element A belongs to R and A dash belongs to R such that A plus A dash is equal to A dash plus A equal to 0. So then it is A dash is called inverse of A. A dash is called inverse of A. And next commutative. So commutative for every element A comma B belongs to R such that A plus B equal to B plus A. So this 5 axioms it will be satisfied the then R comma plus is called abelian group under addition. Okay, and second R comma dot is semigroup under multiplications. So semigroup means it will be satisfied the 2 axioms. The one is closure, the another one associative. So closure means A dot B belongs to R under multiplications. And associative A dot B dot C equal to A dot B plus dot C. So closure associative under multiplications. So these 2 axioms satisfied, then the R comma dot is called semigroup. And third one, distributive law. So distributive law is A dot B plus C is equal to A dot B plus A dot C. and B plus C dot A equal to B dot A plus C dot A. So for every A comma B comma C belongs to R. So totally 5. So this 5 axioms and this 2 axioms and this 2 axioms. So totally 9 axioms. So this 9 axioms, the R comma plus comma dot, the set R comma plus comma dot is satisfy the 9 axioms, then R is called ring. Okay. Next definition, ring with commutative. So a ring R comma plus comma dot is said to be commutative ring. Is said to be commutative ring if A dot B equal to B dot A for every A comma B belongs to R. So in the commutative rings, we can say that under multiplications operations. So A dot B equal to B dot A, that's a commutative property under multiplications. So this axioms, commutative rings satisfy under multiplications, then R comma plus comma dot is called commutative ring. Okay. Next definition, ring with identity. A non-empty set ring R comma plus comma dot is said to be ring with identity. Ring with identity. Ring with identity. Okay, if there exists an element 1 belongs to R and A belongs to R such that A dot 1 equal to 1 dot A equal to A. Okay, so then it is called the ring R comma plus comma dot. We can say that ring with identity. So now we can say that what are the examples in ring. Okay, so now we can say some set of numbers Z. So Z is integer. So Z is integer and R is real number and Q is rational number. Okay, R is rational number, Q is irrational number and C is complex number. It's all our ring. Okay, it will be satisfy the all the 9 axioms. So it is called ring. Okay, what about N? So N is called natural number. Okay, the natural number is not a ring. Why? Because the natural numbers does not contain 0 not belongs to capital N. So first two axioms R comma plus. Okay, that's I can take the Z. I can take N, capital N, that's a natural number. The natural number does not contain 0. Okay, so identity element 0 not belongs to Z. So the identity element and the identity axioms does not satisfy. Also inverse also does not satisfy. So therefore the natural number N is not a ring. Okay. So next we see that properties of ring. Elementary properties of ring. So a ring R comma plus comma dot is a ring. It satisfies the first property. Okay, now say the first property. The identity element is unique. The ring with identity element. The ring with identity element is unique. And second property, also the inverse of a ring is unique. And the third one, so in the ring r comma plus comma dot, the cancellation law, a plus b equal to a plus c, which implies a equal to b equal to c. B equal to c, that's a left cancellation law. And b plus a equal to c plus a, which implies a equal to b, b, b equal to c. C whole. Okay. So these are the properties of ring. Okay. So now we move to the problems. Okay. So this first, totally the ring is 9 axioms. It will be satisfy the 9 axioms. Then for any set, it is called a ring. Okay. So the based on the ring concept, so now we can let us know, see that problems now. Okay. So first problem. First problem, show that the set of So now the first problem, problem based on the ring. So what's the question? Show that the set of ring Z with a binary operation, addition modulo, multiplication modulo, it is defined by A addition modulo B equal to A plus B minus 1, A multiplication modulo B equal to A plus B minus AB. For every A comma B belongs to Z, is a commutative ring with the identity. So now I want to show that the set of integer Z is a commutative ring with identity. So commutative ring means the ring is as 9 axioms. Also it is commutative. Commutative rings means under multiplications also the commutative ring. So 1 axioms is there. Also with identity. So with identity means the third definitions. Already I given the third definition with identity. So that has to be the one conditions. So totally 11 axioms. I want to verify the 11 axioms. Okay. Solution. So first case, first one, Z comma plus is abelian group under addition. Okay. So first axiom, closure. So by the definition of addition modulo, A addition modulo B equal to A plus B minus 1. A plus B minus 1 is clearly is an integer. So it belongs to Z. So closure is satisfied. Okay. So addition modulo is closed. Okay. And second axiom, associative. So take the three elements for every a comma b comma c belongs to Z. So now take left side. I want to verify a addition modulo b addition modulo c is equal to a addition modulo b plus addition modulo c. So this is the associative axioms. I want to verify this associative axioms. So now take the left side. A addition modulo b addition modulo c equal to a addition modulo. So now applying this a addition modulo b condition for in this bracket terms. So b addition modulo c means b plus c minus 1. Again, by the definition of addition modulo, take this a plus b plus c minus 1, again minus 1. So finally we get a plus b plus c minus 2. Now take RHS. So this is LHS. Now take RHS. A addition modulo b and addition modulo c equal to. So by the definition of addition modulo, a plus b is a plus b minus 1. Again addition modulo with c. So a plus b minus 1 plus c minus 1. So a plus b plus c minus 2. So LHS equal to RHS. So now clearly associative axioms is verified. Okay. And third one, identity. So under addition modulo, I want to find out the identity elements. Okay. So A belongs to Z. Let me take A belongs to Z and E is the identity element in Z. I want to find out E. Okay. What is the identity element in this addition modulo? Okay. So let me take identity element E belongs to Z. So such that the identity axiom is A plus E is equal to E, A. So by the identity axiom is A plus E is equal to A. So now by this addition modulo, A addition modulo E is equal to A. In the left side, A addition modulo E by the definition of addition modulo of two numbers, A plus E minus 1 equal to A. And A is cancelled. So E minus 1 is equal to 0. So E equal to 1. So this is the identity element in Z under the addition modulo operator. Okay. And next inverse axioms. So let A belongs to Z and A dash belongs to Z such that what's the inverse axioms? The inverse axiom is A plus A dash is equal to E. I can add two element. Okay, we get identity element. The resulting value is identity element. If it is resulting value, we get identity element, then A dash is the inverse of A. So that is the inverse axioms. So here I want to apply addition modulo operator. Okay, A addition modulo A dash is equal to E. Already I find out E is the 1 and the identity element is 1. Okay, so A plus A dash is equal to 1. The left side we can apply the definition under addition modulo operator. A plus A dash minus 1. Okay, so A plus A plus, I want to find out A dash. Okay, I want to find out inverse element A dash. So A dash is equal to 1 plus 1 minus A, that is 2 minus A. So this is the inverse element. A dash is equal to 2 minus A. It's also clearly is integer that belongs to Z. Okay, so by the given definition of addition modulo, the identity element is 1 and the inverse element is 2 minus A. Okay, inverse of A is 2 minus A. Okay. Next, last axiom from this abelian group, commutative. Commutative. So I want to show that A plus B, A addition modulo B equal to B addition modulo A. So clearly A addition modulo B is A plus B minus 1 and B addition modulo is B plus A minus 1. It's clearly both of them same. Okay. So therefore the first case Z comma plus is a abelian group. Okay. Okay. So next I want to show that Z comma dot is semi group. So next case, Z comma dot is a semi group under multiplication modulo. Okay. So here I want to verify the two axioms, only closure and associative. So those two axioms I want to verify under multiplication modulo. Okay. So closure means, so by the definition of multiplication modulo, A dot B is equal to A plus B minus AB. So clearly is integer. It is integer. So that belongs to Z. So therefore addition modulo is closed. Okay. And associative, take the three element for every A comma B comma C belongs to Z. So here I want to show that A multiplication modulo, B multiplication modulo C, and A dot B dot C. So I want to verify this associative axiom under multiplication modulo. So take the left side, LHS, A addition multiplication modulo, B multiplication modulo C equal to A multiplication modulo. So now I want to apply the definition multiplication modulo A multiplication modulo B equal to A plus B minus B for in this bracket terms. So that is B plus C minus BC. Clear? Again applying the multiplication modulo definition, A plus B plus C minus BC minus product of these two terms, A into B plus C minus BC. Clear? So by the definition of multiplication modulo, A dot B equal to A plus B minus AB. So here I want to apply this definition, A, B plus C minus BC minus and product this two term, A into B plus C minus BC. So A plus B plus C minus BC minus AB minus AC minus ABC. This is a left side value. So now RHS is A dot A multiplication modulo B multiplication modulo C. So A multiplication modulo B is A plus B minus AB, put in bracket, and multiplication modulo with C, again applying these two terms by the definition of multiplication modulo, A plus B minus AB plus C, adding this, and minus A plus B minus AB into C. Now simplified, A plus B minus AB plus C minus product, first product with C, AC, BC minus ABC. And again I want to simplify, A plus B minus AB plus C minus take inside minus AC minus BC and minus to minus plus ABC. So clearly the LHS and RHS, both of them same. Okay. So therefore LHS equal to RHS. So associative, clearly it is satisfied. Okay. So Z comma dot, therefore Z comma dot multiplication modulo is a semi-group under multiplication modulo. So up to this, I want to verify 5 plus 2, 7 axioms. Okay, so next I want to verify the distributive laws. So the distributive law is third axioms. So the distributive law we have is contained two laws. A multiplication modulo B plus C equal to A dot multiplication modulo plus multiplication modulo A dot C, and B multiplication modulo C dot C is equal to B dot C plus, so this is A, and C dot A. So now verify the first axioms. The first axiom, take the left side. Okay, so I want to verify the two axioms. So take the first axiom in the left side, A addition multiplication modulo B addition modulo C equal to A addition modulo, applying this addition modulo conditions B plus C. So by the definition, the given problem B plus C minus 1. So again apply the multiplication modulo definition, A plus B plus C minus 1 minus A into B plus C minus 1. So what's the resulting value? A plus B plus C minus 1 minus a product inside minus AB minus AC plus A. So finally we get A plus A 2A, B plus C, and minus AB minus AC and minus 1. So now finding the values of right hand side, A dot B multiplication modulo A dot C. So applying the definition, multiplication modulo for A and B and A and C. And second step, I want to apply addition modulo operator. Okay, so A multiplication modulo B is A plus B minus AB multiplication modulo A plus C minus AC. So now applying the addition modulo condition. So A plus B minus AB plus A plus C minus AC, okay, minus 1. So finally 2A plus B plus C minus AB minus AC minus 1. So both of them same. So in the distributive law, first condition is clear, is satisfied. So similarly, the second conditions also I want to verify now. So the second distributive law, take the left side terms, B plus C multiplication modulo A. So applying the multiplication modulo condition, first applying the condition for addition modulo condition, B and C. So B plus C minus 1 dot A. The second step, I want to apply multiplication modulo condition for these two terms. Okay, so B plus C minus 1 plus A minus product of this B plus C minus 1 dot A. Okay, so B plus C minus 1 plus A minus AB minus AC plus A. So finally we get 2A plus B plus C minus AB minus AC minus 1. So now RHS of second distributive law, B multiplication modulo A additive modulo and C multiplication modulo A. So in the first step, we can apply the multiplication modulo for this bracket B and A and second bracket C and A, and second step I want to apply the addition modulo operator. Okay, so and B multiplication modulo A is using this condition B plus A minus BA, and C and A is C plus A minus CA. Okay, next multiplication addition modulo condition B plus A minus BA plus C plus A minus CA minus 1. So simplify this. A is 2A plus B plus C minus AB minus AC minus 1. So both of them same. So second distributive law also satisfied. Okay. So totally I want, still now we verify the 9 axioms. So ring is R comma plus is a abelian group. It contains 5 axioms, and R comma dot is a semi group. It contains 2 axioms, and next two laws distributive law. Okay. So clearly R comma Z, Z. So Z is ring, but proof is not is complete. I want to show that the Z is commutative ring with identity. Okay, so commutative means under multiplication modulo. Okay, so go for the next axioms. I want to show that commutative ring under multiplication modulo. Okay, so its axiom is A dot B, A multiplication modulo B equal to B multiplication modulo A. So A multiplication modulo B is A plus B minus AB, and B multiplication modulo is B plus A minus BA. So both of them integer. Okay, so both the values are same. So clearly commutative is also satisfied. Okay, so next I want to verify identity under multiplication. Okay, under multiplication. Okay, so already find out under additive the identity element is 1, E equal to 1, already find out. Okay, so here under multiplication modulo I want to find out the identity element. Okay, A multiplication modulo B equal to A plus B minus AB. Okay, so let ring with identity. So this axioms say that ring with identity. Okay, so let 0 belongs to Z and A belongs to Z, such that A multiplication modulo 0 equal to, so by the definition of multiplication modulo A and 0, implement this A plus 0 minus A into 0 equal to A. For in this case, multiplication modulo 0 is the identity element. Okay, so this is the identity element under multiplication modulo. Okay, so the problem is complete. So totally I want to show that ring. First again I recall this. So first we show that ring, the set of integer Z is a ring. Okay, the ring contains 9 axioms. The 9 axioms clearly is verified. Okay, and next I want to show that commutative ring. So under multiplication modulo it is also showed here. Okay, and finally the set of integer is a ring with identity. So a ring with identity means it will be shown under multiplication modulo. Let me take 0 belongs to Z and A belongs to Z. So A multiplication modulo 0 equal to A. It's a definite multiplication modulo. Under multiplication modulo definition, A plus 0 minus A into 0, the resulting value A. So A belongs to Z. Okay, then the 0 is the ring with identity under multiplication modulo. So the problem is over. Okay, so clearly the Z is commutative ring with identity. Okay. Okay, so now we move to one more problem. So now the second problem is define the binary operation multiplication modulo and multiplication modulo. So same operation multiplication modulo in Z, okay, is defined by x addition modulo y equal to x plus y minus 7 and x multiplication modulo y equal to x plus y minus 3xy for every x comma y belongs to Z. Explain Z comma addition modulo and multiplication modulo is not a ring. So this case I want to show that Z comma plus comma dot is not a ring. Okay, the last problems I proved ring, okay, but this case is not a ring. Okay, same I want to verify the 9 axioms. Okay, so first Z comma addition modulo is a abelian group. First case. Okay, so now I verify the 5 axioms for abelian group. Okay, so first axioms closure. So closure for every x comma y belongs to Z by the definition of addition modulo x addition modulo y is equal to x plus y minus 7. So clearly it is integer. So belongs to Z. So therefore addition modulo is closed. And second axiom associative. So associative, take the 3 element for every x comma y comma z belongs to Z. Okay, I want to verify x addition modulo y addition modulo z equal to, okay, change the bracket, x addition modulo y plus addition modulo z. So take the left side, x addition modulo y addition modulo z equal to x addition modulo. So now implement this addition modulo condition y and z, y plus z minus 7. Again implement addition modulo condition for these two terms, x plus y plus z minus 7 and again minus 7. Okay, so adding this two number, put minus 7. Same this concept, adding this two term, again put minus 7. Okay, so finally x plus y plus z minus 14. Now RHS, x addition modulo y and addition modulo z equal to x plus y minus 7 addition modulo of z, x plus y minus 7 plus z minus 7. So x plus y plus z minus 14. So LHS, RHS are same. So therefore LHS equal to RHS. So clearly addition modulo is satisfy the associative axioms. Okay. Next, identity. So identity element, I want to determine the identity element E under this addition modulo definition. So let me take E belongs to Z and A belongs to Z. such that identity axiom is A addition modulo E is equal to A. The left side, by the definition of addition modulo in the given problem, A plus E minus 7 is equal to A. So AA is cancelled. So E minus 7 equal to 0, which implies E equal to 7. So in this problem, the identity element value is E equal to 7. Next, inverse. So let A belongs to Z and A dash belongs to Z. I want to find out this inverse element. A dash is the inverse of A. So what's the inverse axioms? Under addition modulo, A addition modulo A dash is equal to E. So already found out E value is 7. So the left side, implement this addition modulo condition, A plus A dash minus 7. So minus 7 is A dash is equal to 7 plus 7 minus A. So 14 minus A. So this is the inverse element. A dash is equal to 14 minus A is clearly integer that belongs to Z. Okay, so inverse is find out. And commutative. So commutative is A addition modulo B is equal to B addition modulo A. So A plus B minus 7. So this is B plus A minus 7. So both of them same. So clearly commutative is also satisfied under addition modulo. Okay. So 5 axioms is over. So first part Z comma addition modulo is clearly abelian group. Okay. So second case Z comma dot, that is multiplication modulo. Multiplication modulo is semi-group. Is a semi-group. So semi-group is contain two axioms, closure and associative. So closure means for any element x comma y belongs to Z, by the multiplication modulo condition, x multiplication modulo y is equal to x plus y minus 3xy. So clearly is an integer that belongs to Z. So closure is satisfied under multiplication modulo. Okay. Next, associative axioms for multiplication modulo is for any three element x comma y comma z belongs to Z. This Z is integer. Okay. So the associative axiom is x multiplication modulo y multiplication modulo z equal to x multiplication modulo y and multiplication modulo z. So take the left side, x multiplication modulo y multiplication modulo z equal to x multiplication modulo, and y and z for multiplication modulo is y plus z minus 3yz. Again implement multiplication modulo for in this integer x plus y plus z minus 3yz minus 3 into product of this. Okay, so this is a left side value. Okay, now take RHS, x multiplication modulo y and multiplication modulo z. Again implement multiplication modulo for in this integer. Okay, same element x plus y plus z minus 3xy minus 3xz, same element 9xyz. Okay, so LHS equal to RHS. So therefore, associate is also satisfied under multiplication modulo. Okay, so next, finally, verify the distributive laws. So remember that I want to show that Z comma addition modulo and multiplication modulo is not a ring. Okay. So now verify the third axioms. Distributive law. So distributive law is A addition modulo, B A multiplication modulo, B addition modulo C is equal to A multiplication modulo B plus addition modulo A multiplication modulo C. A dot B plus A dot C. So now take LHS. So A multiplication modulo B addition modulo C is equal to A multiplication modulo. Now implement addition modulo condition for B and C, B plus C minus 7. I can implement multiplication modulo condition for this two integer A plus B plus C minus 7 minus 3 into A into B plus C minus 7. So A plus B plus C minus 7 minus 3AB minus 3AC 21A. So this is a left side value. So now RHS A addition modulo B, but sorry, A multiplication modulo and addition modulo A multiplication modulo C is equal to. So by the definition of multiplication modulo A plus B minus 3AB and addition modulo A and C is A plus C minus 3AC. So now implement addition modulo condition for this two integer A plus B minus 3AB plus A plus C minus 3AC minus 7. It is safe. LHS or RHS are safe? No. So clearly 21A is not there. Okay. So LHS and RHS not equal. LHS RHS are not equal. So therefore the distributive law is not satisfied. So once the first distributive law is not satisfied, don't move to the next two laws. So clearly Z comma addition modulo multiplication modulo is not a ring. Okay, is not a ring. So first axiom satisfied. Okay, abelian group, and second axiom semi group is also satisfied. So the remaining distributive law is not satisfied. So finally, hence Z comma addition modulo multiplication modulo is not a ring. Okay. So next we move to the third problem. So the third problem is a different one. Let k and m be the fixed integer. Find the values of k and m for which z comma plus z addition modulo multiplication modulo is a ring. So clearly it is given ring. Okay. Under the binary operations, x addition modulo y is equal to x plus y minus k, and x multiplication modulo y is equal to x plus y minus mxy for every x comma y belongs to z. So clearly z is ring. I want to find out the constant value k and m. Okay. So main thing is distributive law. So clearly it is a ring. So since it is a z, since z is ring, so clearly it is also satisfied. It has satisfied distributive law. So the distributive law contains two axioms. I take the first axioms, A addition multiplication modulo B addition modulo C is equal to A multiplication modulo addition modulo and A multiplication modulo with C. Okay, so implement these conditions. So x dot y plus C is equal to x dot y and x dot C. So x for so first case implement the multiplication conditions. X multiplication modulo y is x plus y minus mxy. Mxy x plus okay. So first implement this y addition modulo condition. Y addition modulo is y plus z. Y plus z. This is z. Y plus z minus k and again implement the multiplication modulo condition. X plus y plus z minus k minus m into x into y plus z minus k. Okay. Simplify this. X plus y plus z minus k minus mxy minus mxz minus into minus plus mxk. So this is left side value equal to, now we can simplify the right side term. So first implement multiplication modulo x plus y minus mxy and addition modulo. Here implement multiplication modulo for x and z, x plus z minus mxz. So again implement addition modulo condition, x plus y minus mxy plus x plus z minus mxz minus k. So here I will write same thing, x plus y minus mxy plus x plus z minus mxz minus k. So now I want to find out k and m. So now equating the coefficients. So equating the coefficient of x term, equating the coefficient of x, equating the coefficient of x is this one and this one. So this x is cancelled. The one x should be cancelled. Okay. So remaining x term one is there in the left side and remaining one x term in the right side. So equating the coefficient of x here, this x coefficient is mk and this x coefficient is 1. So mk is equal to 1, for which case m equal to 1 and k equal to 1, or m equal to minus 1, k equal to minus 1. Then it will get mk equal to 1. So these two chances, m equal to 1, k equal to 1, or m equal to minus 1, k equal to minus 1. So these two cases may possibility of values of k and m. Okay. So this is a required value, m equal to 1, k equal to 1, or m equal to minus 1, k equal to minus 1. So based on these two cases values, we can say about z comma addition modulo comma multiplication modulo is a ring. Okay. So finally we conclude z comma addition modulo comma multiplication modulo is a ring with m equal to 1, m equal to 1 and k equal to 1, or m equal to minus 1, k equal to minus 1. Okay, so this is a required value. Okay, thank you. Sir.